we take our integral, and integral of dx over x is natural log of x evaluated from x naught to x. And the other side, the integral of negative r over L dt is just minus r over L t. Right? Yeah, evaluated from 0 to t. So this becomes the natural log of x over x naught. The natural log of x minus natural log of x naught is natural log of x over x naught, and this becomes minus r over L t. And then we take the exponential of both sides. E to the natural log of something is a something, so this is x over x naught equals e to the minus r over L t. And let's see, we could even go one more step and write it in the form you would normally see it. X equals x naught e to the minus r over L t. So that is the solution for x, whatever x was. X was the EMF minus I over R. So now let's go and get back from x naught and x to real things. So let's see, at t equals 0, let's think about the real circuit. Let me look at it again real quick. The real circuit at t equals 0, we said we close it at t equals 0. And actually the current right at t equals 0 is going to also be 0. It takes a while for the current to get going in the circuit. So at t equals 0, I equals 0. So that tells us what x naught is. If x is the EMF minus I over R, I'm sorry, if x is the EMF over R minus I, then x naught would be the EMF over R minus nothing. Right? So that x naught is just the EMF over R. You can see that's actually the current that you would get if you had no inductor in there. So now we plug that in to here, and we plug in for x. So x is the EMF over R minus I equals x naught is the EMF over R e to the minus R over L t. And then you solve for I. So you bring I over here, you bring this over here, you divide through by the EMF over R, and you get that I equals the EMF over R times, it looks like this is over here, 1 minus e to the minus R over L t. So the current as a function of time is an exponential. In this case, it's a thing that grows exponentially to a saturated value, not exponential growth, but exponential growth. So let's take a look then at what it looks like. Here's time. Here's time equals 0. Here is the current. And if you plot a function like this, it starts out at 0, because e to the 0 is 1. So it's 1 minus 1 is 0. So it starts out at 0, and it goes up, and it kind of saturates to some value. And at time equals infinity, this basically just becomes a constant. This thing goes to 0, and it goes with a constant EMF over R. So that's the behavior. Now, let's see if it makes sense. Let's go back to the circuit and see if that's what we think would happen. Well, when you close the switch, the current is 0, but it starts to grow very fast. The di dt is very big right when you close the circuit. So since the di dt is big, the dB dt is big, you have a big changing magnetic field, so the back EMF is really big. When you first close the switch, not the circuit, when you close the switch, all your EMF drop is all across the inductor, and none of it is across the resistor, because the current's 0. There's no drop here. All the drop is here. And then, as the current builds, you start to get some of your drop here, and you start to build up a magnetic field here, and it slows down, doesn't change as much. And when you reach steady state, you have a constant current, constant magnetic field, no back EMF, and then all your drop is here. So your potential drop starts here, and it transitions to here, following this equation. So that's the basic behavior of the LR circuit.